All right, just a short check. Hi. So I will talk about the correct by construction protocol Caspar, which was introduced by Vlad Zampi. And especially I will look at the implementation in RChain. So speak up.
Speak up, please.
This is not amplified, it's just for the recording.
Just for, okay,
yeah.
Nice. So my name is Udo Kreaenzien. I'm an engineer by education. I'm normally engineer more in the direction of mechanics, but 3 years ago I switched to numerics, and I'm, no.
Better? Yeah, that's better.
Hi. Could you make it a little bit?
I think you need to stand back a bit.
Yeah. Okay, is this volume okay for you? Nice. So it's actually based in, I'm more based in the mechanics side, but when I switched 3 years ago to the computational side, by doing fluid dynamics, where I focus on direct numerical simulation, which is some tough part within this field, and where research about turbulence and chaotic behavior. Then I got introduced to the blockchain technology 1 year ago, at the beginning of last year, so it's 1.5 to be exactly, and it caught my interest. So now I'm here, and I want to say something about RChain. Why I find RChain interesting was this concurrently design and the scaling by nature. I mean, it's directly links to all what we know about chaotic design. Like, we will later see it behaves a little bit chaotic, by the way. It behaves not like sequential, like one thing happens when the next. No, everything is happening all the time, and the same is in my field, turbulence. So what I will do is, disclaimer, I'm only a messenger. So I won't take any theaters of what you will see here. I visualize for you, I make schemes for you, so that you can understand something more easy than just reading and researching by your own, so I'm condensing, by the way. So just a short introduction to correct by construction from the Caspar protocol. As I said, it was introduced by Vlad Zampi. It belongs differently than introduced, I think it was a spelling error. It's a proof of stake protocol, by the way. So instead of solving a riddle, a very difficult riddle with a lot of computation power, I'm having a stake, which is a certain amount of tokens in my wallet, and with these tokens, I'm betting on certain blocks, for example. So, and if other people, that's just short. If other people join the bet and validate it, this block is forged. Yeah, it's added to the blockchain. So what Vlad made very differently is he solved this nothing at stake problem, because in many of the proof of stake protocols, you had the thing you could bet on an invalid block, and you didn't get punished for it. That means you can do it several times, you can repeat your process, and you don't need to worry about your stake, actually. Other in proof of work, there you need to invest your computational power, which is resource, which is energy, which is your hardware, the processing time you need for it. So there you invest your resources. Now he introduced the process which he simply called slashing. That means if people behave malicious, they get punished. Their stake gets slashed away. He said in the beginning, he said totally slashed away. So that means if you have your 10,000, your 50,000 worth of US dollar worth inside in your stake, and you bet on the wrong block, and somebody finds it out that your justification you sent was wrong, your stake is away. So this solves the problem. You cannot repeatedly torture the blockchain, and you won't have such a strong incentive to try it, because at the first try, your stake is lost. In proof of work, you just shortly switch your resources and then you only pay for your resources, you still have your hardware at home. It doesn't get burned. In this protocol now, it gets burned. It's like I'm destroying your Antminer. If I find out you tried even something which was not valid, the Antminers are gone. So one thing was punishing the validators for malicious behavior, like putting wrong blocks on the, or suggesting betting on wrong blocks. Or, for example, they could also be punished for non-performing, meaning it gets important when I'm offline. So then I'm, and not reliable on the network. And he also introduced, which is not here, equivalence, it's called. When I start to justify one block, and I bet on one block, I could also start to bet on another block in most systems. And the thing is now, if someone finds out, I always need to give a justification why I did bet on this block and why I did bet on the other block. And if I find out that they are mathematically contradicting, this is equivalence, and at this point, your stake got slashed away too. So that's the main part which is important, which you need to keep in head. I will later go more in detail when we talk about the implementation in RChain, which I actually start just right now. So in RChain, we have a concurrent system. And concurrent system means that not every validator is starting at one block and then take the next one and the next one. No, everyone finds blocks. So this is a higher rate, actually, at which we build our blockchain, and a higher transaction rate. So we need to think now how we can bring this how this consensus is now in this namespace property in this concurrently property built in. So the first thing is necessary for our proof of stake system to work is that every validator knows every validator. I cannot slash you if I don't know where you are and who you are. So everyone needs to know everyone. That means we need a main proof of stake contract within our smart contract system where every validator is bonded. So at this top level, we have bonding. That means validators can assign as a validator, or a future validator can assign for a validator. We have unbonding. That means I can say I unsign myself from my validation. And further, the slashing protocol works over this top level. As I said, I need to reach you, so I need to know you, so it needs to be at the top level. So from this top level on, we have many regions or namespaces where RChain works. And every region has a specific local proof of stake contract. And within this local proof of stake contracts, there actually is the rewarding regulated. So that means we do not have rewards and stake at one place. We have the bonding of the stake in the top level, and we have the regulation of the rewards in the local level. That also means if I want to get my stake back, I need to invoke the smart contract at the top. If I need to get my rewards, or if I want them to be calculated, updated, I need to go to the regional level, to the local level, where I'm actually assigned for validating. So in this region, we have, if we have validators in these regions, there might be active validators, which are actually set. Each local contract has a number of active validators. And if this maximum number is reached, then we have also validators in the queue. That means if I want to join and it's already full, I get to the queue. If the queue is full, I get rejected. So in the region, in the local contract, we define, as I said, the maximum number of active validators, the maximum number of queued validators. Why it is so, I already told you. The maximum unbonding rate. So that means if I want to unbond from my smart contract and many others want this too at the same time, then nobody's there. So who's calculating? Who's validating? Nobody. So that means I need a rate to say, okay, you can leave, but please not too fast. On the other hand, we have a post-unbonding stakeholding time, which actually serves at one specific problem, because if we have an asynchronous system like we have in RChain, there's a probability actually that someone has suggested in building a block which is not right, then unsigns from the smart contracts, and then later on jumps again inside after, let's say, like 50 blocks and rebuild on this block. And this is a long-range attack, and this can damage the blockchain. And also we have a minimum bond amount, which is like the minimum stake you have inside, and you have a maximum stake, so that you do not get too powerful, because your vote is evaluated by your bond, actually by your stake. So, and also we have a cryptographic evidence for the performance, which says that you can perform on this protocol actually. Yeah, this information is also known at the top level post-contract, because if I apply for a region, the top level contract needs to know, okay, what are the requirements? And how this is solved, I will explain on the next slide. So for example, if I want to bond, I send a message to a top level contract, which I shortly just call post-contract. And this one checks the message actually. Within this message, I give the information, okay, the region I want to join, so where I join, the form of my ID, which could be my public key. So if I want to get later on my rewards and my bond back, they need to know it's me when I ask for them. A purse, so where my tokens are stored. And I also need a cryptographic evidence, which is defined by the local contract. So this will happen sequentially, actually. So after our proof of stake contract gets this message, he first validates, okay, is the purse empty or is there something in the purse? For example, somebody could open just a lot of requests, this is the demand of service attack, but with no value within the purses. So I got a lot of requests within our blockchain for validating this this question of our future validator, or wrong future validators. So if his purse is empty, he gets a rejection. If it's valid and I have something in my purse, then I check, okay, good, how many people are already in this region you want to work? So at this moment, the top level contract requests information of our local contract. And if, for example, the maximum number of active validators is reached, nothing more is evaluated, and the future validator is directly put into the queue and later re-evaluated again to save computational power. So if there is enough space, we go right away. Maybe I should use the pointer. So here we were going down, queuing of the applicant. And now we have 3 places as active validators. And at that point, we check, okay, are you able to join? Do you have a proof for this local contract? And if this proof is invalid, it's actually taken as an attack. At that point, the tokens are deduced if there are any tokens on the wallet, which should be at this point. So the top level contract deduces the tokens from the wallet and of course rejects. He won't allow it at this stage. But if his check of the cryptical proof is valid, now the staking amount or the bond is checked. So if it is in the right range, it's valid. If it's not in the right range, it gets rejected. And if it's valid, we are finished nearly. So the tokens are finally bonded. The validator and bytes are cryptographically documented in the parent block. And the validator is added to the region or to the local contract. Yeah, so this DOS attack we had. So what is the second one? If I want to bond somewhere, I want to start as a validator and I want to quit at some point as a validator. So this works differently. I'm now already a validator. I now invoke an unbond with a message where I put some certain arguments inside. These arguments are the signature of a block after which I want to unbond, and also the channel where I want to receive my stake, my bond back. And yeah, this is sent to the top-level contract again. This top-level contract then checks the unbonding rate of a region. Yeah? If too many left, he rejects and say, no way, we need you to validate there to keep the blockchain part alive, the part alive of the blockchain. If it's valid, the validator is unsigned, and now the place is free. So if the maximum active validator number is reached, and there's now a place free, that also means that we possibly have somebody in the queue. Now, randomly, someone of the queue is chosen to take his place. This is the action between. And then begins the post-staking time. What's the post-staking time? It's what I mentioned. We want to avoid long-range attack. So, but if you unbond and I give you back your money, what do you risk? Nothing. Your reward maybe, but it's less than your bond, possibly. So, in order not to give an incentive or to give you an incentive to do a long-range attack without being punished, which is some of the main aspects of this protocol, you have a post-staking time like, okay, your stake is here until, let's say, for 100 blocks. So after 100 blocks, we say, okay, you get your stake back now. Because at this point, it's highly uncertain that something went wrong. At this point, when we reach our limit, a purse is sent to the X-validator, so he gets his bond back. But from this bond is deducted some amount of slashing. Differently than prior suggested, the idea now is not depending on the fault you cause, and not to slash all your amount of a bond. So some faults might be minor, and there you can say, okay, only 5%, only 10% of your bond is slashed. The rest you can still use. The next one is, I want to slash somebody. Now, I know how I bond, I know how I unbond, but in order to keep the system safe, to punish somebody, there needs to be a punisher. So every validator who is in the system is able to slash another validator. And this we do by finding errors in the justification. So this process works like we have a validator A and B. Validator A invokes a slash with a message. In the slash, he says, okay, the ID of the offender, validator B, the malicious one, I have here. And then the signature of the accuser, that's me. And then the offense description, like roughly speaking, okay, you said at this point, and then there follows this block after this block, but that's not true. Actually, it was this block. But you stated your opinion, you didn't change it. So this was your fault. Cryptographic evidence of the offense, so documentation could it be, and a purse return channel. So now it gets interesting. After invoking this slash, the post contract checks the evidence. If it's invalid, validator R gets slashed, and his coins get deduced away. So this should build a barrier to people who wants to earn money by slashing and not by staking or minting or And if it's valid, the accused validator B is slashed. Validator A gets a purse with a slash amount. So I can earn money if I find something who behaves not nice. That's a secondary channel of income, actually, which where we hope, okay, there's an economic interest in people finding other people who is malicious. The contra is here at this point. Well, I said we have a post-staking time. That means we have a time where you cannot unbond. Now, if I slash you and I get the amount of your bond, the total amount, I can off-chain, I can say, hey, I slashed you, I get your amount, and I give it back to you. So this is a way to circumvent this post-staking time. This still is a contra, and they are working on it, how to solve it. Nothing is fixed at this moment. There are first versions online, but they still get improved. So, what are /able events? /able events are a breach of service level agreement. That means if I do not perform right or perform well, if I have too many offline time, I get slashed. Maybe not the whole amount, but some amount. Then the production of an invalid block, which will be highly sanctioned, and equivocation, which also will be highly sanctioned. So equivocation, as I said, is like I'm putting two arguments. Now, this whole system works with arguments, with justifications. And then on the blockchain, there are certain messages. One time I said this one thing, the other time the other thing. And like I said before, this is contradiction. This can be mathematically proven. And then at that moment, I did an error, and this error is actually high. So it's a high problem for the blockchain, because at this point, you can change the blockchain to an invalid point. So this is /able events. And now it's interesting, yeah, okay, if I stake something, I want to get a return, which is my reward. This is on the local level. Everything I told you before was on the top level. Now we switch to the local level. And at this point, again, the validator invokes an for example, if I want to update my reward. Now, the local contract I need to know what's the level of my actual reward right now. So I need to update it somewhere to write it in a block. And for this, I invoke an update with a message to my local POS contract of the region where I'm working. This checks, okay, good, are you really from this region? Is it justified? At this moment, and if it's valid, it updates the validator's balance. It also updates the balances of other validators. No? If I'm starting to calculate for some blocks the fees, the returning fees or the minting amount, I can also start to calculate it for the other ones. So, and this balance, this update of the balance or the reward is now calculated by a discount times the transaction fees of the certain blocks. And what's the discount? What's the sense behind the discount? Now, for example, I can start my own region, and I can start to, stake there. We call it staking at this time. And then I can build many blocks or suggest many blocks behind each other consecutive. The problem is when I do it consecutive, I have no cooperation with the other nodes, with the other validators. And the discount now, it's actually a factor which decreases with increasing consecutive blocks. That means it gives me an incentive. Left. I'm nearly finished. Yeah, okay. This gives me an incentive to cooperate with other validators. So, yeah. Yeah, and of course I provide a signature where I can identify it. Otherwise, everybody could write this message. So now the only thing left is our payout. If I want to be payout, I again send a message to the local POS contract. The local POS contract again checks the content of it. If it's valid, yeah, okay, you get your payout sent to your purse. Hey. Well, it's the last slide actually. You get a payout sent to a purse sent to your channel you provide, and this. Okay, nice. That's better actually. Okay, I sent my ID and I sent my purse return channel, and if it's valid, I get a purse with a reward amount of rewards I built up or I staked in the system. That was it. No, sorry. Yeah, okay, that's an idea we need to talk about actually. It's propositions. So the original idea of the CSP Casper protocol was that I set my bet on a single block. But now we want to build a scalable solution, a solution which can process a higher amount of transactions And by this, I need a different solution than only picking one block, another one. And additionally, we have concurrency. That means not every node knows when a block comes, actually. And they would need a long time to communicate which was the first one. And this would lower our rate. Now, in order to higher the transaction rate, I can give propositions. For example, like, I saw this block, and I know the other one block, it came afterwards. And then I can put a bet on it. And I can make this n times with a length of n. Based on the weight of people who bet on the same line of blocks, like 20 blocks in a row, which came after which one, this gets confirmed by the system. Yeah? And by this I can, by not focusing on the single blocks, I can indeed higher my transaction rate. So this is an example. The thing is, in our concurrent system, we also have a possibility that blocks merge. And we do not only have one chain, one side chain or one fork, and that was it. We have also the possibility they come back. No, they split again, they come back. We have 3 side chains. They merge together again. And this is a simulation visually.
Let's not do it. We have to go.
We have to finish?
Well, yeah, show it again.
Show us.
Yeah.
Yeah.
That's 4 seconds.
Yeah, I cannot, but where I can.
Yeah, here.
Oh, okay.
It's like a different
Oh,
screen.
okay. Nice. Okay.